to welcome our final speaker of the day, Khashayar Filom. He's a postdoc at the University of Michigan, and he will be speaking on entropy behavior of real rational maps.
Thank you, Kitty. So since I'm the last speaker, I think we should all thank the organizers, Kitty, Noel, Ben, and Ivan. Thank you so much for organizing this. It was a great day. Thank you so much. Okay, so I'm going to talk about the entropy behavior of real rational maps. And so I'm going to first give you an idea of like what I'm trying to do. So the question is about the entropy, and we are like mostly doing one-dimensional systems. So in the first talk, we encountered some of like interval maps and their entropy. And here, so the entropy, the type of entropy that I am interested in is the topological entropy. I'm going to talk mostly about topological entropy, which is like you have the usual interpretation of it as the complexity of your system. And the difference here is that I am going to ask this question: how this topological entropy varies in a family of interval or circle maps. So I'm not just looking at one system, I am looking in a family of systems. Okay, so there's a nice interpretation of entropy when you deal with interval or circle maps. And there is like this theorem of Milnor and Schlenk. I mean, you can like take it as a definition of topological entropy if you don't have the definition in mind right now. So suppose I have like a map of interval or a map of circle. Suppose it is continuous and multimodal. So multimodal means that you have like finitely many local extrema. So there are like finitely many monotonic pieces. And then the theorem says that the topological entropy of such a system is the exponential growth rate of the number of laps. And by lap, I mean a monotonic piece of such a thing. So here, for example, you have two monotonic pieces. This is a unimodal map. Then you iterate, you get 4. Then you iterate, and you consider the if you like iterate one more time, you get like 6 monotonic pieces. And then the question is, what is the exponential growth rate of these numbers? And this theorem of Milnor and Schlenk says that the exponential growth rate of the number of monotonic pieces is the topological entropy. And if you have like a circle map, how to make sense of monotonic pieces, in that case, you need to like lift it to an interval map, which will probably have discontinuities, but that's also okay. So we have this nice interpretation of entropy, and now we want to see how it changes as the map varies in families. So maybe the first interesting example, maybe this is like the simplest example of a nonlinear family, is the logistic family. So I'm considering basically quadratic polynomials, but like the normal form I am considering here is a bit different from the normal form that Mary considered in her talk. So here I am like writing them in this form as a logistic family rather than like x squared plus c. And another thing is that I am sticking with the real maps. Okay, so there are two interesting pictures here. The first picture is this bifurcation diagram. So maybe some of you have seen this before. So the way that this picture is produced is by following what is happening to the critical point. So the critical point here is 1/2. And by following what is like happening to it, you see that, for example, at the beginning, it is absorbed by a fixed point. In other words, you have like an attracting fixed point, then attracting 2 cycle, attracting 4 cycle, and so on. So the whole period doubling cascade. And there are like these windows here. So after the first period doubling cascade, you see like these parameters where it seems that the critical orbit, the orbit of 1/2, behaves differently. It is not absorbed by any attracting cycle, but then again, occasionally you see these things which we call periodic windows. So they are basically hyperbolic components. And I'm really glad that hyperbolic component came up in Mary's talk. So here, hyperbolicity, so for these windows where you see like the critical orbit getting attracted by a cycle. Here, the hyperbolicity is meant in the sense of complex dynamics. So we mean that the critical orbit is converging to a cycle, or an attracting cycle. So the cycle will be attracting. And each of them comes with its subsequent period doubling bifurcations. So the difference here with Marie-Stokes is that I am just thinking about real hyperbolic components. Okay, so you see this very rich bifurcation behavior here. And on the right, you have a graph of the topological entropy, or the exponential of topological entropy. So you see that in the beginning, like when you are here, the topological entropy is 0, the exponential is 1, and then it picks up and it goes until you reach 2. So at the very end, when A is 4, your system is conjugate to the full 2 shift, and the entropy will be log 2. So here, exponential is 2. Okay. And so there are two observations here. The first is that the entropy is increasing. Remember, we want to see how entropy varies in families. And then the next thing is that although it is increasing, you see all these plateaus here. So it is not strictly increasing. And that makes sense, because whenever you are in one of these hyperbolic windows, or like, for example, you have an attracting cycle absorbing your critical point, the entropy there should be the logarithm of an algebraic number. And so because of the continuity, it should remain constant. So for example, in a hyperbolic window here, and also on the subsequent period doubling cascade, you have just one entropy value. And so you see all of these plateaus, all of these flat parts on this entropy graph. Okay, so let us just record these two observations about the entropy function for the logistic family. The first one was that the entropy is increasing. You can even say that the number of laps of an iterate is increasing with the parameter. So this is something about the nature of bifurcations here. But although it is increasing, it is like a devil's staircase. It is not strictly increasing over any open subinterval. So each of these things is a deep theorem. The first one is called the monotonicity of entropy for quadratic polynomials, and it is proved by Milnor and Thurston, and also by Duadi, Hubbard, and Sullivan. For the second part, so I told you that whenever you have like these hyperbolic windows, that we expect the entropy to be constant. So in order to like convince you that this like graph can never be strictly increasing, it is enough to say that these hyperbolic parameters are dense. And this is another deep result. This is Fatou's conjecture for real maps, and it is proved by various authors. Okay. So you see that just for this simple nonlinear family, how rich the literature is and how thoroughly this is studied. So another very deep result is the work of Jacobson and Liubich. So
Khashayar, can I ask a quick question?
Sure, sure.
Which is so the previous picture, can I think of that as kind of like a Cantor-Lebesgue type function? I mean, it's got all these flat pieces. Does it have, it's just this exp of entropy, like, or should I think of it as, I mean, does it actually have these kind of continuous pieces?
This picture?
I mean, it has the constant pieces, but whenever it's increasing, it's kind of not continuous, right? Is that right? Or is that
no, this picture is continuous. Entropy is continuous. Okay. Yes, it is continuous. But I mean, it is monotonic here, but it is not strictly monotonic.
Got it. Thank you.
Sure. Okay, so just to give you another result that tells you how thoroughly these families are studied. So Jacobson proves that there is a positive Lebesgue measure of stochastic parameters, which are like completely opposite of those hyperbolic parameters. So stochastic parameters are parameters for which you have an AC. The map admits an absolutely continuous invariant measure. And of course, you cannot have that if you have an attracting, if you have a basin of attraction. And Liubich, it is a very deep theorem of Liubich that tells you up to a measure zero subset of parameters. This is a dichotomy. So every parameter is either like hyperbolic or is like stochastic. Stochastic meaning that there is an AC. Okay, so the key thing that we want to study in this talk is this monotonicity problem. So this like the fact that you have an increasing graph for the entropy function. This is what we are interested in, and we want to see if it holds for like more of in a more general setting. Okay, so in the more general setting, so the first thing is to think about higher degrees. What if instead of quadratic polynomials, I consider something else? So in that case, I need more parameters to describe a system. And so the first question is how to make sense of the monotonicity of a function on to monotonicity of function which is multivariate. So if you think about it carefully, a function of a single variable being monotonic means that its level sets are either points or intervals. And points and intervals are the only connected subsets of the real line. So to make sense of monotonicity of a function which has more than one variable, you can define the monotonicity as the connectedness of the level sets. And the level sets are called isentropes here. Okay, so the goal is to like set up an entropy function on some space of dynamical systems and then discuss the level sets. So there's a conjecture of Milnor for polynomials of degree d. It says that for any d greater than equal to, the entropy function is monotonic on the parameter space of degree d polynomial maps of the interval. So the example I gave you, the logistic family, was where d is 2, and now this is a general conjecture that generalizes that. Okay, so I have put polynomial maps into quotations because I am talking about a specific family of polynomial maps. I am dealing with maps that are first boundary anchored, and then they have a real distinct critical points. So if you think about it, that family of logistic maps, x goes to a times x times 1 minus x, had that property, right? And why this property is a useful one? This property is useful because you can then use your critical values to parameterize the space of such polynomials. So we are going to need that space because we want to set up an entropy function on the space of like interval maps or like some space of dynamical systems. And so we need to have a method for think about that space of dynamical systems. So this is like a very convenient property that allows you to like have an understanding of what is the space on which you are considering the entropy function. And as we shall see shortly, in the setting that I am going to talk about later, things are not that simple, and the space is going to be much more complicated. Okay, so this conjecture here is a theorem proved by Baron and Van Estrian in 2009. So this is like the proof is complicated. This paper is published, I think, in JAMS. And they proved this theorem in this setting for polynomial maps with real critical points. Okay. So what I would like to do is to consider, instead of polynomials, quadratic maps. And again, let us do the least possible degree, which is real quadratic maps. And so I am here doing, I want to do rational maps. So instead of a polynomial, I do a ratio of polynomials, which is going to be a rational map. And then in the case of degree 2, my question is, can the same statements about the entropy be made or not? So here is the main result. So I am talking about like real quadratic rational maps, like the ratio of 2 quadratic polynomials instead of just one polynomial. And the main result is that this entropy function on the moduli space of real quadratic rational maps is not monotonic. So things are different from polynomial setting. But there are some dynamically defined regions where this entropy function is monotonic. And keep in mind that monotonic here is what I define. Monotonic means that you have connected level sets, connected isentropes. Okay, so I need to define so many things before getting to the proof of this thing. I need to first tell you what do I mean by this real entropy of rational maps. Then what is the space on which this real entropy is considered as a function? So I told you about the moduli space of these dynamical systems. What is that space? And then when we talk about real quadratic rational maps, there is a very nice description of their moduli space, and I'm going to talk about that. And finally, this result was based on experimental evidence. So we did some numerical simulations and some entropy counterplots that just directed us toward this theorem. So I'm going to also show you some pictures of entropy counterplots. Okay, so this is the the main goal is to like tell you how this result works. Okay, so first I need to do a bit of groundwork because as I said, instead of polynomials, I am doing rational maps. And how things are going to be different if instead of a polynomial, we consider a rational map like PZ over QZ. So can a similar question about isentropes be formulated or not? So if you have a rational map, meaning like an endomorphism of the Riemann sphere, which is holomorphic, and say its degree is d, then the topological entropy of that guy is going to be log d. So this is due to Lewis, and it is like a special case of the theorems that you have about the entropies of like holomorphic maps. If you have like a projective variety, if you have a morphism of that, people have studied what is the topological entropy. And so here the topological entropy in this case is going to be log d, the logarithm of degree. Okay, so it seems that here we don't have anything interesting because all these systems are of the same entropy. But I mean, if you add an extra condition, some interesting subsystems emerge. So if I assume that my map is with real coefficient, then the map keeps real line union infinity invariant. And I can discuss the dynamics and the entropy on this real line union infinity, which is basically a circle. So I'm going to just focus on real rational maps, and then I can define this real entropy. So I am looking at taking a rational map with real coefficients, meaning like a ratio of two polynomials with real coefficients. I am looking at the topological entropy for the restriction of f to this guy. And this is going to be in the interval between 0 and the logarithm of degree. So the first thing that you see, which is different from the polynomial setting, is that now you are dealing with a circle map because real line union infinity is a circle. But for example, in the example of the logistic family or in Milnor's conjecture, we were dealing with interval maps. So of course they are more complicated. Okay, so this quantity that I defined, which I call real entropy, the next step would be to treat this as a function on some appropriate space of dynamical systems, because remember, the goal is to study its level sets. So now I am going to set it up as a function on some space of dynamical systems. So what is that space? So I'm going to set up this real entropy function as something continuous on some moduli space of real rational maps. So what are these notations here? So first, the moduli space of complex rational maps is shown here by MDC. D is the degree, and this is just a space of Mobius conjugacy classes of rational maps of degree D. So this is the central object in like holomorphic dynamics and in arithmetic dynamics. So I consider all rational maps modulo Mobius conjugations. Okay, so there is like this is like very well studied. And since I want to do maps with real coefficients, I look at the locus in this space, which is determined by real maps, and I have called this M prime D. So maybe I can like set up my real entropy function on M prime D. I just told you what do I mean by the real entropy of a map with real coefficients. I just look at the restriction to the extended real line and I take the entropy. So the way to define this is to like take a point of the moduli space and then take a representative and then look at the real entropy of that representative. But the issue here is that the map is not going to be single valued, and that's the reason that I have included this dashed arrow here, because you are picking representative. So remember, this space is a moduli space. Any point here is a conjugacy class of rational maps, and I'm picking a representative. So the issue is that you may have like two maps. You may have like two maps that are real, but they are conjugate only over complex numbers. So they are Mobius conjugate, but for example, restricted to the real line, they have totally different dynamics. And so they give me different entropy values. But hopefully this thing only happens over like a positive codimension subspace. So if I threw out something which is called the symmetry locus, I end up with a continuous well-defined real entropy function. And this symmetry locus is just a locus of maps with non-trivial Mobius automorphisms. So if I just threw away something, I end up with a real entropy function on some moduli space of real rational maps of degree D. And then I can like,
Sure.
Yeah.
Sorry, could you clarify how you can be conjugate on the Riemann sphere by an element of PSL2C, but not on the real slice?
Yes, for example, you may, so one example is consider Z plus 1 over Z. And then suppose the conjugation, suppose, for example, and then consider Z minus 1 over Z. They are conjugate. So if you like, for example, a scale by I, so Z plus 1 over Z. If you just scale by I and then divide by I, it becomes Z minus 1 over Z, right? Think about it. IZ plus 1 over IZ, and then you divide by I, it becomes Z minus 1 over Z. And then over the real line, the dynamics are totally different.
Thank you very much.
Thank you. And then this is like, but this is like a very a special situation because it only happens like the example that I told Roland about, Z plus 1 over Z is an example that the map admits non-trivial symmetries. So I can like just disregard them, throw them away because they are of a large codimension. And then I have like end up with this entropy function. And so if I just threw away something of positive codimension, I end up with a real entropy function. And it is continuous, so the continuity is technical. This is due to Mizerevich, the continuity of topological entropy. Okay, so I should like tell you more about this moduli space because that would be the space in which we want to discuss the level sets. So the moduli space, the complex moduli space of degree D rational maps is, you can like think of it as a complex orbifold, you can think of it as an affine variety, it is of dimension 2D minus 2. So Silverman constructs it through geometric invariant theory. For our purposes, since we want to do quadratic rational maps, we only consider the case that D is 2. So the case that D is 2 is where, as I told you before, we have a very nice description of this moduli space, which is due to Milnor. So from now on, I am assuming D is 2, and I'm going to say what Milnor did about this space. So when D is 2, you are doing quadratic rational maps. And Milnor identifies this space, this M2C space with the plane C2. Okay, how it works. Think about like a quadratic rational map like PZ over QZ, where P and Q are polynomials of degree 2. How many fixed points you have? If you like solve for fixed points, you need to solve a cubic. You need to solve for ZQZ minus PZ is 0. So there are 3 fixed points, and then associated with any fixed point, you have a multiplier, lambda 1, lambda 2, and lambda 3, that tell you about the local behavior near your fixed point. And so Milnor shows that you can identify M2C with the plane via considering the symmetric functions of these 3 multipliers. And why I am only considering the first 2 symmetric functions, the reason is that these multipliers are related to each other with a fixed point formula. So the important thing here is that the fixed points come into play. You have a quadratic rational map. There are 3 fixed points. I mean, there are cases that like they may collide, but counted with multiplicity. There are 3 of them. You consider their multipliers, and then these 2 numbers give a coordinate system on the moduli space of quadratic rational maps. And since we were talking about real maps, real quadratic rational maps, I need to tell you what is the corresponding space M prime 2. So M prime 2 turns out to be the underlying real plane. Okay, so the goal then would be to have a real entropy function on this space R2, and then I'm going to tell you about that theorem that I mentioned before. Okay, so to summarize, in the general setting, there is a bit of work necessary before setting up an entropy function on the moduli space of real rational maps of degree D. So the domain, this M prime D minus S prime, is an irreducible real variety of dimension 2D minus 2. Dimension, I mean the real dimension here. Then you have this function, which is well defined. This is the topological entropy over this circle R union infinity. This is surjective and continuous. And then this domain of it is disconnected because the domain, there are like different topological degrees for these circle maps. And so you have different connected components here. Okay, so you have now a well-posed problem. What are the level sets of this function? So if I want to study the dynamics and the real entropy of rational maps, the question, the first thing to answer in analogy with the polynomial case would be to ask what are like the level sets of this guy over the connected components of this domain. Okay. And as I said, we will as I said, we are mostly interested in the case of D being 2 real quadratic rational maps. So from now on, I will assume that D is 2. And so I'm going to show you a picture here. Okay, so as I told you, due to the work of Milnor, M prime 2, the moduli space of real quadratic rational maps, can be identified with a plane. So here the coordinates are that sigma 1, sigma 2 coordinate that were defined in terms of multipliers of fixed points. And what are different colors here? So the thing that I threw away, which was like maps with like additional symmetries, is now a cubic curve that you have here and also here. And if you remove that curve, because that's the place where the entropy function is multi-valued, if you remove that, you end up with 3 different connected components. And these connected components correspond to different topological degrees. So here in this blue component and yellow component, the critical points are complex conjugate. There are 2 critical points. We are talking about a quadratic map. There are 2 critical points. And so if they are complex conjugate, you have a covering map on the real line union infinity. The entropy is like log 2. And if you threw them away, you end up with this pink part, which is the interesting part. And we want to like talk about how the entropy level sets look like in this pink part. And there is like a finer partition here. So you see these words unimodal, bimodal, monotone increasing. I'm going to talk about them later. So we have this picture. Then I'm going to show you the numerically generated entropy counterplots here. And then we are going to talk about whether they are connected or disconnected. And also keep in mind that this is like a moduli space. So any point that I pick here, it corresponds to a conjugacy class of maps, not just a single map. Okay.
Khashayar?
Yes.
Hi.
Hi.
Then that picture, there's a beautiful picture.
Mm-hmm.
So the axes, are those your sigma 1 and sigma 2?
Yes. Yes. Those are sigma 1 and sigma 2. And the picture is adapted from Milnor's paper. I just added colors here. Okay. So let us now, from now on, concentrate on the case of D being 2. This pink component that I showed you here is the component of degree 0 maps. Let us see how that comes into play. So there's a simple dichotomy. You have like a quadratic rational map, and you have either two complex conjugate critical points. So the critical points are off the rear circle, in which case you have a covering map, and its topological entropy is therefore log 2, right? So that's like that theorem of Mizurovich and Schlick. If you have a covering of any degree, then its topological entropy is the logarithm of degree. Okay, so suppose the critical points are real. In that case, we can get rid of this issue of dealing with circle maps. It is not hard to show that when the critical points are real, in which case this map here is of degree 0, it is not hard to show that in that case, the image of this map is just an interval. It does not cover the whole thing. And so you can just concentrate on this interval maps. You can just concentrate on the restriction of F to its image. And so we are dealing with circle maps we are dealing with interval maps from now on by considering these, but these are not boundary anchored anymore. And so among all those three among all those three connected components of this M2 prime minus S prime that I showed you, only where the component where the critical points are real is interesting, and we call that the component of degree 0 maps, because then this map is of degree 0. And so if we go back to this picture, here entropy is log 2, here it is log 2, and I'm only interested in this pink part, where you can think of it as critical as like quadratic maps whose critical points are real. Okay, so what is this finer partition that you see here? So you have like a map with real coefficients, and there are real critical points, and then you can condition on whether the critical points also lie in the image of real map or not. So I am like here restricting my map to F of R hat, and then the question of how the critical points are situated with respect to F of R hat tells me that that question tells me how, what is the modality of this map. That tells me what is the modality of this map. And so based on that, you see the unimodal part where there is just one critical point in F of R hat, then two bimodal parts, and where you have no critical point, then the map is monotonic. Okay, so we have this picture, and now in the pink part, we want to understand how the entropy level sets look like. And as I said, the only interesting part is this unimodal part and these two bimodal parts, because you know that for an increasing map, for a monotonic map, the entropy is 0. Okay, so let me finally show you some entropy contour plots. So the entropy contour plots that I show you are generated in this pink part. And of course, as I said, this middle rectangular part and these two parts are the interesting ones. So here's the first one, the entropy contour plot in the unimodal and minus plus minus bimodal part. So minus plus minus is the orientation of the map, meaning that it goes as decreasing, increasing, decreasing. So this is the entropy contour plot. This is like the coloring scheme. And so the reason that these points are scattered here is that this is a moduli space, so I had to create the contour plots in some parameter space and then project them here. So the projection map is nonlinear, and then some points here fall apart. But you shouldn't interpret this part as like a disconnectedness of level sets. So here, as you see, any region of the same color, they all remain close together. It doesn't break. For example, you don't have two blue regions or like two purple regions. And so you can conjecture that restricted to these two parts, the entropy function is monotonic. Okay. So what else? There is this other bimodal part, plus minus plus bimodal part. What happens there? So this is a different entropy contour plot for that region. And so here you see something completely different. So you see that, for example, you have a red region here, you have another red region, here you have two disjoint yellow regions. And so this numerically generated plot tells us that the monotonicity here fails. And it actually fails due to a non-polynomial behavior. I'm going to try to say what this non-polynomial behavior means later. Okay, so the algorithms to generate the entropy counterplot are here. So this is also an interesting computational problem, how to write an algorithm to find the entropy of an interval map. Okay, so let me go back to this picture. So I told you that for these parts, these covering parts here and here, entropy is log 2. For the the monotonic parts, the entropy is 0, and it is only these two bimodal parts of different orientations and this middle rectangular unimodal part, which is interesting. And our conjecture, based on the plots that I just showed you, is that here in these two adjacent regions, the entropy is monotonic, and here it is non-monotonic. So I'm going to tell you how these things work. Okay, so I think I should wrap things up. So I will try to at least tell you why we believe here the entropy fails to be monotonic due to a non-polynomial behavior. So what polynomiality has to do with any of this? So remember that the entropy is monotonic over polynomials. That was the result of Milnor and Thurston, and the polynomials lie here as a line. So over this line, the entropy is monotonic. Okay, so this monotonicity result that I'm going to give you is really by reducing everything to the polynomial situation. So here is a theorem. So you have, that's like the picture that I just showed you. The conjecture was that over this minus plus minus bimodal region and over this unimodal region, over the union of them, the entropy is monotonic. And my theorem here says that below this line that you see here, over this green part, the entropy is monotonic. So I completely show that it is monotonic over minus plus minus bimodal region and over a part of the unimodal region. So what is this line? This line has a dynamical significance. This line is where one of the fixed points become multiple. And just keep that in mind. So my theorem was that the main theorem I gave you at the beginning was that there are some dynamically defined regions where the entropy function is monotonic. And this is dynamically defined because this line that separates yellow from green is where a fixed point becomes multiple. Okay, so, and here we expect the entropy to be non-monotonic. Okay, we get to that. I don't have enough time to get to the whole details of the proof. I just tell you this. So when you have three real fixed points, one of them should be attracting by simple computation, and then you can do a quasi-conformal perturbation and turn them into polynomials. So this is the line that parameterizes polynomials over which we know that entropy is monotonic due to Thurston and Milnor, and also Duadi, Hubbard, and Sullivan. So the idea of proof is that over this green part, we reduce everything to the polynomial situation. Okay, so what about that non-monotonicity result? So remember, the conjecture was that here, over this yellow part, the entropy is not monotonic. And also, before going to the next slide, also remember that we conjecture that over this whole rectangular region, the entropy is monotonic. But the theorem that I gave you just proves that partially over this green part. Okay, so this failure of monotonicity is proved in another paper. This is a joint work with Kevin Pilgrim, where we show that the restriction to this other bimodal region, plus minus plus bimodal region, admits a continuum of disconnected level sets. And why we call this a non-polynomial behavior? Because you cannot pull off that technique of perturbing and attracting fixed point into a super attracting fixed point and make things polynomial. So this non-polynomial term is coined by Milnor in another paper where he discusses bicritical rational maps. So he calls these maps essentially non-polynomial, and the reason is that all fixed points of them are repelling. And so in that situation, you have a different dynamics. You can have disconnected entropy level sets. Okay, so finally, I think I have, Kitty, I think I have 1 more minute, right?
Maybe 30 seconds.
30 seconds. Okay.
If you want to
So
just
just
wrap up,
two very recent papers. These are like from 2 months ago. So remember that I told you that we want over those whole rectangular thing, middle rectangular space of like unimodal maps, we expect monotonicity, although my theorem proves that partially. So this is just recently proved independently by Yang Gao and also by Bonifant, Milnor, and Sutherland. So this is just like for 2 months ago. So for example, for this family of maps, over like this particular parameter space, you have unimodal maps, and then the monotonicity that you see in this entropy counterplot is just recently proved. And finally, the conclusion, the basic conclusion was that these circle maps have a much richer combinatorics compared to interval maps, because that monotonicity of entropy here fails, because as you can see, the point was that you have this non-polynomial behavior that makes things much more interesting. Okay, thank you.
Okay, thank you so much, Khashayar. Let's thank the speaker. For time reasons, we're going to go ahead and just move to the breakout session. I know